Welcome to the second part of the discussion with Jim Weninger. In this episode, we will be discussing gravitational lenses and the cosmic web. Now, before we start, again, I'd like to say a huge thank you to all of my Patreon supporters and those that support me via PayPal. If you are interested in that, then there's more down below in the description. But for now, enjoy the second part of the discussion with Jim. If that is true, and you would have to argue that there must be galaxies that eject material directly towards us.
Right, but then we wouldn't be seeing it as a high redshifted quasar. We'd be seeing the same thing, but maybe attributing that as like just the.
Well, what would we see it as? That's my sort of question, and that sort of, in a sense, comes back to this whole idea: is what is the difference between a galaxy and a star, and are there examples of galaxies that, I don't know, maybe they're not galaxies? I mean, M49 is a bizarre one when you look at it, because, we can't resolve the stars inside of it, and I don't, there are elliptical galaxies where we can. I don't know, is it possible that what we consider to be an elliptical galaxy, particularly when we look at M49, is that an example of something like this? That it was, and this sort of ties into this idea of sort of an evolution as they sort of move outwards. But if it is ejected directly towards us, maybe we should be looking for something that we misclassify as something else.
Right.
And I don't know what that would be, because we don't really know what quasars are. And that comes back to my sort of point of, do we know what the differences between a galaxy and a star? I mean, sure, okay, we know that galaxies are made up of lots of stars. But again, if this idea of a fractal universe holds, then things at different scales must behave in similar ways. And I'm not saying that a galaxy would have tufts and, produce light in the same way. I'm more saying that what is it I'm saying? That effectively our assumptions of what galaxies are, when we look at them in the sky and we label them as a galaxy, may not always be a galaxy in its broader sense. Like, if the core of the galaxy is a quasar, if that's the beginning point, the highly energetic, which ends up being whatever it is in the nucleus of a galaxy, and is that, when we look at M87, is that what sits at the heart of it? Maybe. But then equally, you look at M87, and it has a massive jet that sort of pours out of it, and we look at, young, what they would consider to be young stellar stars that also produce jets. And in my mind, those jets look pretty identical when we compare the two. At what point do we say that they are different? If they behave in a similar way, then I guess I'm going around in circles here. But my point is that, and there's something I've said before, we need to start looking at some of the peculiar galaxies to identify exceptions to our thinking, because I think we're very much in I guess the way the human brain works, but we look for patterns, and what we assume is a galaxy, I don't know whether it always is a galaxy, is my point. And I think if something was coming towards us and it was indeed ejected from it, at some point, some of it might be gas, and at some point, some of it becomes something else. And yeah, I'm waffling now, going round and round in circles, but I think you understand what I'm saying, right?
Yeah.
So, and I think all of that also comes back to this whole idea of distance. If we look at all of the maps, when we look at these beautiful images that we see that map where our galaxies are, and they're all based on redshift. And if because one of the interesting things that Arp talked about was that if you removed redshift, then actually what you should be looking at is sort of the apparent magnitude of some of these objects. And comparing that apparent magnitude to the redshift gives you good indication of where it sits. And it paints a very different picture of, I guess in some sense, how big our universe isn't in terms of what we can see. Now, you could argue, because I know that he did look at some of the deep field images when he was, in his book, when he talks about the arcs and the gravitational lenses, but I'm not sure that he had access to all of the latest images. But certainly when you look at some of those deep field images, the question is, how far really does it go? If we look at some of these, all of these, and when I looked at some of those gravitational lensed images, and well, let's pull it up, because I do, having sort of reread his book, and you look at some of these. So I think this is the one that and this is not the one, but one of the ones. I kind of look at these in a different way, because what if, as Arp says, they're not lensed images, but in fact that they are material that is being ejected or that is connected. And you look at this and you go, well, that doesn't make much sense, right? Because why would it curve all the way around, and why would it connect to this? That doesn't make any sense. And why do we have blobs along here? And the more that I think of it, the more that to me does make sense, that there are these points of compression along some of these lines that cause it to start forming new objects.
There's observations for sure you have to be aware of, and it's where the redshift isn't quantized. That's to try to explain whatever theory it is, explain why it isn't for the quasars, but not for like those lensed galaxies. If what we think are lensed galaxies, if those are really shells around the galaxies, then those aren't quantized. So we have to explain why why are quasars quantized, but not just.
Do we have enough data on the redshift of those lenses to be able to say that it's not quantized? Because if you look at his quantization work, he certainly found it in galaxies. Galaxies show this, BL-like objects show it, and quasars show it. And I just wonder, when you look at some of these, how... I have no idea what the redshift for...
Well, actually, that would be an interesting one to research, just not from Arp's work, but from... The mainstream does have a huge set of these lensed galaxies, and it would be interesting to see what the redshifts of those are.
Yes, because
even continue that work just on.
Because I'm until I see it, I don't know whether it is or isn't quantized. So I don't know how many data points you've seen for these, but I would be not at all surprised to find that it does follow the same quantization. When we look at this, I would expect it almost.
Yeah, that'd be interesting to see what. Again, it'll just be the all you have to look up in the mainstream is just the distances of these objects, and see if there's any, because they're going to interpret the redshift that way. So we should just see like quantized distances then too.
For me, one of the clues is the fact that they obviously claim that this is the 12 times image, that the galaxy is repeated 12 times, and if I sort of switch that around, that implies that they get the same redshift 12 times
right
around. So that does sort of match this idea that if this is a shell, then it, you would expect that redshift to be the same.
The same for the whole, right?
For the whole ring, yeah. And okay, there might indeed be, and this comes back to the question I was asking about, what is the difference between, how does the quasar itself form? Could it be that there is some interaction at this, if this is indeed just a boundary layer that causes the formation process? So are we seeing in these images, and I'm using a little bit of imagination here, but if the assumption is that everything scales, then a galaxy is a larger version of a star in some sense of the word, then could it be that there are objects that are even larger than galaxies that would do the same thing, but the amount of material that they eject is just so much more? Or is it just a very large version of a galaxy? Because is it possible that these dots that we see here are that sort of clumping formation in a long stream, that this material is moving outwards, and whatever causes that sort of initial punch to form it is happening all along this filament that moves outwards? Whereas when we look at some of the more normal galaxies, you would only ever get one because it's a very narrow beam. But for some reason, the amount of material ejected here is so large that you get multiple points of this, which is why they all look the same. Because, we look at a quasar and they all look the same. You can't look at one and say, oh, there's a red one or there's a blue one, or, we can't really resolve them. They look the same because that's sort of... I don't want to say it's primordial, but it's sort of so bright that we can't make out any detail on it. And I just wonder whether that's what's sort of going on along this filament. It's a question. I don't know. There's this. It sort of makes me re-examine some of these images in a totally different way. From the fact that we do see this reflection across here and a magnification. Is that more to do with the structure is creating a similar shockwave on both sides, and therefore that mirrors what happens on one side to the other side? I don't know. This is the image where if you cut and paste, you see those two on this side with those 4 cyan colored stars on the inner side, and you see it matched along the edge. But is that maybe more an artifact to do with what's going on? If as you say, this is some sort of a boundary that the material sort of pushes up against. If there's a large amount of material, then maybe that's its sort of effect, like we see in where's that image?
Yeah, it could still be a lensing effect by that. Remember in Dowday's work,
yes,
he's showing that plasma double layers do, that would be a plasma double layer, maybe not in the gravitational field like he modeled, but that's still a double layer where you'd see that imaging then, and that again, that would be the same one then causing the red shift, though. It would be the electrons.
It's interesting always as well that there is this difference between the sort of the reddy and the bluey colored ones. If you look at the other one that I did, so you have these blue dots, and then you have the red, blue and red, blue, and again you similar sort of this dot placement. See that 2, and then sort of spread across. I don't know. Sometimes you see what you want to see, and I'm kind of aware of that. But when we look at here, you have that similar sort of. I don't know. I just think there's.
Is there any pattern to the blue and red compared to the inside or outside of that curve, or not really?
In this one, it's less I mean, in this one, there's like a very strong red band across there, and then these tend to be blue. And then you have this, again, this to me reminds me of Arp's Peculiar Galaxies, because it's just kind of stuck in the middle of this, but yet it still matches a similar sort of color as those out here. And then you have this, almost like there's another lensed image within that. But again, here we have the red, and then we have the blue. But equally, you have these galaxies that have that as well. And looking at some of Arp's Peculiar Galaxies, some of those had a similar sort of dotty blue character. Some of those, particularly the ring ones. Where's that one? The one they did on the Stars Like Galaxies. Yeah, here. So you got the blue, and you got your red. Again, I don't know. You know, you can read a lot into some of these images, but yeah, I think some. I mean, look at this galaxy. How smooth that ring is compared to that one. I mean, it's in no way matches that image, the gravitational lensed image, but some of them, you just look at them and you go, yeah, that's a galaxy. Just very peculiar. Some of them are more obvious. But I don't know. I think you're right that you know, when we look at these images, it could actually be a combination of things that's going on. That if this is sort of ejected material outwards, is then, interestingly enough, when you look at the center, we do indeed see something at the center. I don't actually know what that is. I'd have to do some research to find out what object sits at the center of this image. And I'd have to do some experiments to see how well it sits at that center. But that's, yeah, you'd say it might be coincidence. What about this one? Yeah, maybe this sits at the center. I'm not sure. It does sort of look like it. More looks like the center's about here. So I don't know. It is interesting in some of them how some of the galaxies align to the sort of orientation of the circles. And at first you sort of think that's, you know, even out here, you sort of think that's just, you know, your mind playing tricks on you. But if it is true that this material gets ejected outwards, then maybe that's not so crazy. Maybe that does make more sense. I don't know. I could spend hours looking at these images.
Yeah.
Be none the wiser. And the fact that this is, the red line goes, you see it sort of like distorts around the circular bit of that galaxy. Yeah, I think there's definitely merit in the idea that you know, it's ejected material, but whether that explains all of it, I don't know. And as you say, you know, Dowdy's concept of refraction through plasma, you know, would make sense as well, because these shock waves would then also be higher electron density. So you'd have that to account for as well. But the flip side of that is that if that is the case, if we do indeed see shock waves as sort of higher electron density points, then would we not expect to see the objects that sit on these to have some sort of distortion?
Distortion in what way?
Like refraction, like we're seeing in these images.
Well, see, the thing about Dowdy's thing that's interesting is that it doesn't lead to like a wavelength dependent. It's not like simple refraction. Like he shows that all the light will be bent at angle. He calculated what it was for the sun, for example, but that was wavelength independent, and that we have to have that. It can't, because we don't get like these. We'd never have clear imaging through that if it wasn't that kind of bending, which is what works in, like what's right about at least the mainstream idea of gravitational bending is that it does the same thing to all the light, no matter what wavelength. If it really is the curvature of space, it's curved as much as it is. So that it has to be something like that is independent of wavelength, and that's one thing that Dowding's work does that's really important. It bends light, but doesn't really cause that breaking up into the rainbow of spectrum.
No, and I guess you could argue for these quasars that there might be not quite point light sources, but that's sort of the way we could treat them. Therefore, the lensing effect on this would be, well, it wouldn't be. I mean, again, you could argue that the mainstream concept of lensing of a quasar is exactly this: the fact that you end up with, an Einstein cross. We don't see that. We don't see distortion in this image, but maybe that's because, well, I guess the interesting question is what electron density would be required to cause enough distortion, and would we, if it is a narrow band that we are talking about here, that we are looking through, and the object sits within this, then the distortion, well, would the distortion be even enough that actually all you're seeing is just a magnification of that object? It just looks larger, it just looks brighter, which is effectively what we're seeing because they are super bright objects, without it necessarily causing enough distortion to create this sort of an effect. And maybe when we look at this image here, then maybe we're talking about electron densities that are even higher, that would cause more of a distortion for whatever it is that is within that field of view or within that band of material. It has to be, like, if we are explaining this as a a Dowdy effect, then you would equally expect that Dowdy effect to occur to some extent here. And, well, would that be a reason why, if the object is ejected directly towards us, so from here, why we don't see it as a quasar? If Dowdy's effect is actually happening here, and all it's doing is causing a magnification, making it look larger, making it look brighter, then when we see one that we don't see it through this long slit where you have more opportunity for magnification, but you're seeing it through a much thinner bit, is that we would just see it as a dot, and therefore you ignore it because that's not a quasar. Just a thought.
Yeah, again, it would be good to look at examples of galaxies that seem to be ejecting something that's not a quasar.
Yeah, like a radio source or an X-ray source that we don't identify as an object. It's just a diffuse area from which we're identifying that it belongs. Because there are examples in Arp's work of and that could be that they've just not gone back and measured it, but it could also be the fact that it is too small for us to measure, and then we just see why would it be diffuse and not? You'd still expect it to be from a point. I mean, that to me is another weird piece in Arp's work, is when he looked at the gamma rays and the cosmic rays. That was another massive piece of the puzzle for me, in terms of the fact that a lot of so this is gamma rays are actually not coming from the objects themselves, but from the diffuse cloud around it. And that's telling, because that suggests that it's the material that is connecting these that is energetic, and not necessarily the objects themselves, which is sort of goes along this idea of these shells as well then. And cosmic rays as well. You know, when you look at cosmic rays, the same. You know, and the idea of cosmic rays, you know, how do we explain it in the EU concept? And you're talking about, you know, double layers, collapsing double layers. I'm not saying that these are necessarily collapsing, but see what I'm saying? That maybe what we see as X-rays and gamma rays from these objects, maybe it's not just the object, but it is the fact that it's coming from the boundary layer that contains other material, electrons, protons, or whatever, as well as the object that sits at the center, which is why when you look at the gamma ray map, that it appears, you know, more diffuse. And also why when we look at the cosmic rays, so look at where cosmic rays come from, cosmic rays, then the majority of them come from the Virgo cluster. Surprise? Not really, because if they are expanding shells, that's a lot of double layers, and, you know, maybe cosmic rays, speculating, is the interaction between different double layers. Don't know. Just putting it out there.
Yeah.
So I think, you know, if you look at the collection of all of the stuff that ARP does, there's enough there to make you question many of the things that we assume. But equally, I think there's still so many more questions that it asks. It doesn't. I think you have to take his evidence as a sort of a starting point, not as the solution. I don't think he had the solution to all of it. But I think it certainly points, you know, many fingers in terms of, you know, redshift does not equate to distance. Our idea of the structure of our local neighborhood is way different from what mainstream are telling us. And that there is this concept of sort of a life cycle that these objects go through, and that there is a lot of evidence to suggest that these objects are what is responsible for the, you know, X-ray and cosmic rays that we see, not necessarily the objects that we define as quasars, but these larger structures that they connect into. And connect, because again, if you look at a lot of his images, you know, they show this massive connection across, you know, again, this is looking at the Virgo group, M49 and M87, and then all the way down to these other quasars that sit down here. You know, and they were all sort of connected. And I think this is X-ray. This image shows X-ray contours. And that to me suggests that they are part of this much larger structure that connects them together. But there is this, for me, there is one caveat in, well, it's not a caveat in his work, but a caveat in one of the assumptions that we make. And that is to do with the cosmic web. Because the cosmic web is based on, correct me if I'm wrong here, but it is based on that redshift data in terms of where objects sit, and the fact that that means that there are these filaments that they sort of draw the line that connect material together, and that it sits at these particular distances. Am I right in saying that?
Right. They obviously aren't putting, like, the observations show all these, you know, scales of filaments, but I don't.
Yeah, like there's one is the Able group. There's one that they, you know, they think that the Able group sits on sort of the edge of one of these bigger structures. But my sort of caveat in my head is that, you know, we often talk about the fact that it shows the sort of higher level structure. But again, if you look back at Arp's work, then actually a lot of that reasoning that goes into thinking that there are these larger structures, and whether you call them walls of galaxies or whatever, is based on this sort of quantization of some of that redshift. The fact that you find it at only particular points means that material must be collecting, and therefore we have these huge walls of galaxies. Well, if redshift is not equated to distance, then, well, I'm sorry, but we don't have that. And then this notion of a bigger structure doesn't necessarily exist. And I think Arp's view was very much, what we see at the moment is sort of our local. I don't want to call it local neighborhood because that has its own sort of connotation, but we're within this sphere of what is visible, and that there might be material that exists much further away, but that we just can't see because it's obscured by all the stuff that sits in the way. Yet when you look at mainstream, they use the idea of redshift to explain that the universe is, a certain distance wide, and that we can see a certain distance or age, whether that's, I think the oldest object is about 13 billion years old that we can see. But if redshift isn't to do with that, then actually those distances become much, much shorter. And some of those are really quite close. And some might be further away because, again, it's sort of to do with looking at the apparent magnitude. But our idea of scale is way different if you look at redshift in terms of being intrinsic versus distance. Then it brings a lot of objects a lot closer together. Now, that doesn't mean that the universe itself is puny small. It means that what we can observe is much smaller. It might indeed still be that the universe is infinitely large. We just can't see that far,
right.
It could well be that when you look at a deep field image, you're seeing some of those objects that maybe are further away. And then this goes back, I guess, also to, and I don't know whether it fits in with the plasma redshift, but certainly the idea of tired light, which, if you look at Tom van Vlaanderen, he sort of built that into his models. The fact that, light will also, he used it to explain redshift. So I need to be careful with trying to mix too many of those things up. But the idea that light itself would not travel forever, that there would be material that obscures it, material that absorbs it, and therefore, whether that's dust or other things, if the universe is big enough, there's no way you're going to be able to see everything all at once. But obviously those that sort of say that sort of disproves itself, because if the universe is infinitely large, then that material eventually, given enough time, would heat up to such a high temperature that it would become visible. And also we would also be burning to death because all of that light, when you add it all up. But obviously that makes the assumption that light can travel forever and not be absorbed, and that heat energy or the energy that is absorbed by the particles can't go elsewhere, which I think when you look at Tom van Vlaanderen's concept is a nice way to have he had it was the boundary between the light ether and the gravity ether caused a friction, and that absorbed some of that energy, and that way you could have a sort of a recycling of the energy between those two, so that the gravitons could release some of that energy into the light ether, and light could leak some energy back into that. I think, from memory, I think that's sort of how it worked. And to me, that comes back to the idea that what we see is on a much smaller scale than what the mainstream tries to predict. And I think my point, because I've waffled so much now that I've lost track of my point, but my original point was that those large structures that they talk about probably don't exist, which would include, in my mind, but correct me if I'm wrong, the cosmic web.
Yeah, I should look at how much of the structures they're seeing with, from compared to actual observations, like of dust clouds that you can see connected to, compared to, look, you're saying walls of galaxies, but if it was quantized redshift, the only way it would be like see walls would be if they were aligned kind of. We wouldn't be able to see down along walls. We'd be able to see walls like propagating towards or away from us, or fronts.
Yes. Like, I think one of the ways he describes it in his book is effectively, if you look at the whole idea of quantization in terms of galaxies and also quasars, it puts us at the center of a series of explosions in order to explain that in the mainstream. Because you can't have got that material to those exact points unless it was part of a shock front that sort of moves outwards. And yeah, I mean, I think that probably does need more research, but my worry is, it's not a worry, but at the back of my mind there's a niggling thought that, you know, when we look at those larger scale structures, that actually they may not be in the same way as is described by mainstream, because of this idea of redshift. Because the further away those objects are, the only way that they can see them, the only way that they can measure the distance, it's got to be redshift, right? There's no other way that we're going to be measuring the distance to them.
Right.
Logically speaking. So that again, I guess you could argue, does everything have an intrinsic redshift or not? If it's hydrogen gas that they're measuring a redshift, well, they have to be measuring it because something is passing through it, surely. It's not going to glow itself unless it's energetic, but that's not the cosmic web. It's pretty invisible, I thought. You know, we're seeing it based on like you said, gases and other things, and that sit sort of in front of galaxies, or that connect to and through galaxies. I mean, I'd love to be able to draw a picture of what the Virgo cluster looked like if you ignore redshift. And Arp sort of alludes to it in his book, but he doesn't actually provide any sort of picture, because he draws the connection between the Virgo cluster and the Centaurus, and then that through to us. You know, that potentially there's like a hierarchy between those. And the one for me question in which comes back to chicken and egg, I will admit, if Arp is correct, and that M49 is the first galaxy in the Virgo cluster that sort of seeded all those that you see around it, where did it come from? Because again, if this idea is that one galaxy creates another galaxy, which creates another galaxy, then something has to have created M49, right? There has to be some, and maybe we can't see it. You know, maybe you're talking that those lines would be much further away, but that is, and that got me thinking about the cosmic web, because I kind of thought, well, maybe they're just points on the cosmic web that then, for whatever reason, seed like a starting point, and then it sort of spews off like a leaky pipe. You know, normally the pipe is fine, but all of a sudden you nick the pipe and material starts spewing out, and that creates new material, which creates. And then I started to worry about, well, what if the cosmic web, you know, if you think it's all on redshift, that doesn't exist. But yeah, so that's for me sort of an enduring sort of mystery is what creates that seed spark that would have caused M49 to start, which is similar to the you know, the question about what seeds a star, and brings me back to this whole idea is what is the difference between them, because the mechanisms, if we're dealing with plasma and we're dealing with pinches, the mechanisms have got to be similar. So what initiates a star, surely that initiates a galaxy. And therefore also what we see in terms of the formation of a quasar into a galaxy would effectively also have happened to M49, but whatever mechanism that happens is whether it's a pinch point or a seeding event. It's for me still one of those sort of mysteries, I think. But it still, for me, it still all makes sense within an electric universe. But it's, rather than talking about the fact that, a galaxy forms, it is identifying the fact that there are seed galaxies, that there are, and it makes sense because, again, you look at galaxies and superclusters of galaxies, they all form together. And weirdly enough, if you look at the cosmic web, and this comes back to your point that we may be able to identify, particular paths that flow into galaxies, but certainly one of the things that they identify is that clusters of galaxies form at the boundaries between cosmic filaments, where they join together. And that's no coincidence, right? So you've got, if they are, or were flows of plasma that sort of meet, well, at the junction point, maybe that's enough to start like M49 off, which then sucks material out of that filament and starts spewing material out, creating the quasars, which create M86, which then creates its own stream, which creates M86 and M89, etc., etc. But again, I don't often see people putting all of that together in a form that's digestible. Not that what I've just said is in any sense digestible, but you know what I'm saying.
Mm-hmm.
But yeah, the beauties of I guess looking at these things, I think, is more questions than answers, but it still makes sense in my mind. What art presents makes sense. I can't explain why all of it happens all of the time, but there is a logical sequence that when you look at his evidence, I go, yeah, I see that. I see it and it makes sense. And you look at some of the concepts of the EU, you get, yep, that all sort of fits together. That makes sense. But it's finding the mechanisms and being able to pinpoint the finesse of how that might happen, and then looking at the bizarre galaxies and explaining, well, in that case, what we're dealing with is, X, Y, and Z. That's still missing for me. And probably will always be missing. Let's be honest, it's not like we're going to answer all of the questions about the universe ever. I think the more that you dig, the more that you will find. But yeah.
And if it really turned us out that it's infinite in scale, then we don't even know if we're looking at in every scale we do see waves of, density, and for all we know, the visible part of the universe could be a very dense region of, or very underdense region of what's out there.
Yeah. I hope you've enjoyed this discussion. So potentially there is a third part to this, which would focus on, again, the scenario where the quasars are coming towards us and what that potentially might look like, and whether our understanding of galaxies is correct. As always, be brave, be curious. The truth is waiting for us. Until next time.